Welcome to iLecture Online, and here's another good example for you on how to apply electrical potential and electrical potential energy. So let's read the problem. It says here that we have three charges. We have a 4 microcoulomb, a minus 6 microcoulomb, and an 8 microcoulomb charge, and they're placed at the corners of a square with sides equal to 1 meter. How much work is required to do so? And when they say that, when they ask that question, how much work is required, it's the same thing as saying, what is the potential energy of the system when you're done putting the charges in those locations? All right, so let's draw a square. There we go. And we're going to place charges at 3 of the 4 corners. Now, it doesn't really matter which 3, where you're going to place each one. What corner, you can place this one over there. Matter of fact, it might make a little bit of a difference. Yeah, I guess it does depend. I'll take that back. It does depend where you place them, but let me just place them wherever I decide to place them, and that's just a good example of how you do a problem like this. All right, so the way you do that is you start placing the first charge anywhere you like. So let's start with the 4 microcoulomb charge and place it right there. So we place the 4 microcoulomb charge, it's a positive charge, so we'll call that Q1 equals to 4 microcoulombs. And the question is, how much energy did that take? Well, it turns out since there were no other charges present, meaning there's no potential at any location there, it takes absolutely no work to get it there. So the work to place the first charge in a location at one of the corners is simply equal to 0 joules, because there was not yet any potential there and therefore did not require any potential energy. But now you're going to take the second charge and place it at one of these corners. So let's now take the second charge and place it over here. That's a negative charge. So we call that Q2, and that's equal to minus 6 microcoulombs. Now, there you're going to need to do some work, because the first charge being there will cause a potential to exist at this location. So the radius over here, let's call this radius R1. We can then say that the potential at this location right there due to that charge is equal to K times Q1 over R1. So here we're calculating the potential V1 at this location due to the presence of that charge. And there's the equation. So let's go ahead and well, actually we can wait a moment. And then you realize that the work to put the second charge there will simply be then the potential at that location times the size of the second charge. So we can say that work to put the second charge there is equal to the potential due to the presence of charge 1 times the charge you place in there, which is Q2. And the potential at this location due to charge 1, V1, is equal to K Q1 over R1. That's equal to the potential over here. Let me put it in parentheses so you can see that's the same thing. And we'll multiply that now times Q2. So that's the energy the system will have, or the work that it takes to put the second charge in that location. Let's now plug in the numbers. So that's equal to 9 times 10 to the 9th newtons meters squared per coulomb squared times Q1. Now Q1 was 4 microcoulombs. That's 4 times 10 to the minus 6 coulombs. Q2 is the second charge. Oh, does the sign matter here? It definitely does. These are not vector quantities, these are scalar quantities. And so when you place a negative charge in the presence of a positive charge, there's actually a force of attraction. So that means you'll end up with a negative work done, or negative potential energy, so a minus 6 times 10 to the minus 6 coulombs. And take the whole thing divided by the distance between them, which would now be 1 meter. Remember, that was a square, 1 meter by 1 meter. All right, my calculator here, let's calculate what that is equal to. So let's see, actually we can kind of do that in our head. We have 10 to the 9, 10 to the minus 6, 10 to the minus 6. That would be 10 to the minus 3. And we have 9 times 4 is 36 times 6. That's 108, that's 216. So that's a minus 216 times 10 to the minus 3. And that would be joules, or 0.216 joules. All right. See, I was schooled in the old days when we didn't have calculators, and they made us do some of this math in our head. So, yes, somebody just alerted me that I did make a mistake, and this should be minus because we have a minus there, it's a minus there. Remember, it was negative energy because we're bringing a positive and negative charge together. See, my old schooling failed me in continuing to put the negative sign where it belonged. All right. Now, we're going to place a third charge, and let's place a third charge over here. That is now going to be a plus 8 microcoulomb charge, and let's say that's now Q3. Now, notice we're bringing a third charge into a location that's affected by the previous two charges that are already there. So this charge will cause a potential to exist over there, and this charge will also cause a potential to exist over there. So work 3, or the amount of work we need to do to put a third charge there, will depend on the previous two charges already being in that location. So we're going to have a potential over here due to charge 1, and we're going to have a potential there due to charge 2, and so we're going to find the energy of the work done to place the third charge there by multiplying the potential of the first charge by this charge plus the potential of the second charge by this charge. So that means that we're going to take the potential from charge 1 at this location times Q3 plus the potential from this charge, we'll call that V2 times Q3. Okay, remember, V1 was the potential at this location due to the first charge, and V2 was the potential at this location due to the second charge. All right, so this is equal to V1, that would be K, Q1 over R1, R1 being this distance right here, right, the distance between Q1 and the location of Q3. And we multiply that times Q3. And we add that to the potential over here to the second charge. Now notice this distance right here is R2. That's the diagonal of the square. And so here we get K times Q2 divided by R2. And we multiply that also times Q3. And that's the energy it takes, or the work that it takes to get the third charge placed at that corner. So let's plug in the numbers. So this is equal to 9 times 10 to the 9th newtons meters squared per coulomb squared times charge 1, which is 4 times 10 to the minus 6 coulombs, times charge 3, which is 8 times 10 to the minus 6 coulombs, all divided by 1 meter. That's the distance between those two. And to that I add 9 times 10 to the 9th newtons meters squared per coulomb squared times Q2. Q2 is now a negative 6 times 10 to the minus 6 coulombs. And let's see here. Q3 is 8 times 10 to the minus 6 coulombs. And the whole thing divided by the square root of 2 meters. The diagonal of a square that's 1 meter by 1 meter is the square root of 2. Okay, plugging in these values into a calculator. Again, this is 10 to the minus 12, 10 to the 9, that's 10 to the minus 3. 4 times 8, that's 32, times 9, that would be 320, minus 32, that's 280, plus 8, that's 288. So and that would be all positive, so 0.288 joules. Now this is going to be a negative quantity because I have a negative charge there. So again, because the presence of a negative charge, there's a force of attraction between these two, so it takes negative work to bring it here because of the presence of that charge. And since I have a square root of 2 in the denominator, I'm going to use my calculator for this. So we have 9 times 6 times 8, and we're going to divide that by 1,000 and divide that by the square root of 2, and I get 305, so that's minus 305 millijoules, or minus 0.305 joules. And then if we add those two together, plus 288 minus 305, that looks like it's a minus 0.0, that's 1217 joules. So it turns out, due to the presence of this negative charge and this positive charge, it actually takes negative work to bring this charge over there. All right, so now the final solution then is we add the work it takes to place the first charge there, which is W1, which is 0 joules. the work it takes to place a second charge there, which is a minus 0.216 joules, plus the work it takes to put the third charge there, which in this case is a minus 0.017 joules. So the total work is simply work 1 plus work 2 plus work 3, which is equal to 0 joules minus 0.216 joules minus 0.017 joules. So finally we can say that the total work to place the 3 charges like that is going to be a negative 0.233 joules. And that's how you use potential energy and electrical potential to solve a problem like that. Hopefully you've seen some good examples here, and that will help you do your homework and help you get some understanding of how to apply these things. All right, good luck with these.